In this section, we are going to talk about the solar resource. This slide from Dr. Richard Perez at SUNY Albany shows the relative size of the various energy resources. Dr. Perez is one of the scientists who has been measuring the amount of solar energy for the past couple of decades, so he's a real expert on it. The numbers for fossil fuel resources on the right are the total known quantities. The renewable resources quantities are for each year. And of the renewable resources, the solar resource is by far the largest. So let's see. If you had to bank on one of these for the long term, wouldn't solar be the obvious choice? The much touted forever supply of natural gas is a tiny fraction of just 1 year's worth of solar energy. The ballyhooed Marcellus Shale, it has enough gas to serve the USA for just 2.5 years. And the solar resource is going to last probably for at least another 5 billion years. So what? We tear up the landscape to drill for this tiny amount of natural gas? And while there's a fairly large amount of coal by fossil fuel standards, do we dare burn it all and continue to increase the CO2 in our air to unprecedented levels? Do we dare to continue an uncontrolled experiment on Earth's climate when this place is our only home? Now then, there's the extraterrestrial embarrassment problem. And this is the problem where, if there's any ETs out there and they're cruising by planet Earth and they're looking down and asking themselves, are we intelligent or not? And what do they see? They see us awash in mass quantities of solar energy. And what are we doing? We are burning things. I'm not sure we're going to get into the Galactic Federation. So, when you hear someone say, there's not enough sun, laugh. So the resource is huge. Now another thing that we often hear is that there's not enough physical space to run everything with solar panels. It doesn't require calculus to figure out that the amount of solar cell area it takes to generate a certain amount of kilowatt hours is not that big. The math you learned in 4th grade gets you there. So let's check it out. Whip out those calculators. The USA electricity usage is 4 trillion kilowatt hours per year. The area of photovoltaics, or PV, that it takes to generate this amount is about 4 trillion kilowatt hours divided by 1,500 sun hours times system efficiency. This 1,500 number, this is the average of the NREL irradiance across the US. That equals 3 billion kilowatts of PV. If we use Trina 230 watt modules, the number of modules is, let's see, what's that? So I took the 3 billion divided by my 0.23 kilowatt, that's the size of the module, and I ended up with 15 billion modules. The size of each one is 17.65 square feet. So the square foot area of the total modules needed to power the USA is 265 billion square feet, and there's 10.76 square foot per square meter, so I converted that to square meters. Okay, there's a million square meters per kilometer. Dividing that to get the answer in square kilometers, I end up with 24,698 square kilometers, which is roughly the size of 2 Nevada test site and range. 2 times the Nevada test site and range. So not that big. This would do 100% of the USA electricity, and even if we start using a lot of electric vehicles, there's still going to be plenty of physical space for solar panels. So again, when people start saying, oh, there's not enough space, they don't know what they're talking about. So check this out. In the last calculation, we figured out that you would need close to 25,000 square kilometers of solar panels to power the whole US, so that's 100%. But we already have quite a lot of hydropower, which everybody loves because it's relatively clean and renewable, but it does take a lot of land area. In 2004, the land area for hydropower was about 100,000 square kilometers. That's 4 times the amount of PV it would take to do 100% of the nation, and that 100,000 square kilometers of hydropower only provided 7% of the electricity for the nation. This next slide shows us what physical area of solar cells it takes to run the entire planet. And this is basically showing 0.07% of the world land area would be needed to power the entire world for electricity with solar cells. That's 7/100% of the land area. Now, maybe you can see why the other energy industries are spending so much money touting their stuff and constantly putting down solar is not viable. Their only hope is to keep people in the dark about the solar resource. Bringing this closer to home, let's suppose we wanted to power the entire state of New York with photovoltaics. Can we do it? Are there enough places to put PV modules? Well, right now, about 3% of the state's land area is covered with buildings, parking lots, and roads. The amount of PV needed to power the whole state is 0.75%, or 0.75%. That is less than 1/3 the area currently covered with buildings, parking lots, and roads. Of course, we can build large fields of PV, but much of the load can be served by putting it on existing roofs. And just think of all those hot parking lots that could get shade and generate electricity. Then there are the miles and miles of unused medians along the interstate highways. A typical big box store roof can hold 1,000,000 watts of PV. So again, plenty of physical space to do much of the electricity in New York with solar energy. Getting down to the details of the solar resource data, these numbers come from the National Renewable Energy Lab, or NREL. They took data for 30 years to get these averages. The least sunny spot, Seattle, that in the continental United States, gets 60% of what the sunniest spot gets, which is Phoenix. Every place in the US gets more sun than the sunniest place in Germany, and well, this is embarrassing. Germany is the world leader in deployment of solar power. You can check out the data on the solar resource at www.nrel.gov. There's also a more recent database for about the past 15 years. So a mountain of data on how much sun there is. Let's just take a look at these numbers for a minute. Binghamton, which gets 1496 kilowatt hours per square meter per year of solar energy, is not that close to the bottom as we often think here in Binghamton, that we have a lot of clouds, but it's not bad. Seattle is definitely less sunny. Of course, Phoenix is very sunny, and San Diego, that we think of as a very sunny place, turns out that Binghamton actually gets 73% of the amount of sun that San Diego gets. The difference across the whole country is not even half. So in other words, there's no place in the continental U.S. that gets half the amount of sun of some other place. In fact, the cloudiest place, Seattle, gets 60% of the amount of sun the sunniest place gets. Having less sun in any given spot drives how large of a solar array you need to generate a certain number of kilowatt hours. So for example, in Binghamton, if you need 300 square feet to get a certain number of kilowatt hours, you're going to need a smaller amount in San Diego because they have a little more sun. Here's a pretty picture of a large solar power plant in Germany powering a village. This slide shows a few stats on Germany as compared to the United States. The sunniest place in Germany gets 1,250 kilowatt hours per square meter per year. And remember, Binghamton has 1496. Germany has 17,000 megawatts of photovoltaics installed. The United States is closing in on 3,000. Now, the United States does have an additional few thousand megawatts of other types of solar, such as the mirror arrays that heat a engine at the top of a tower. So Germany has about 2.47 times as much area of land and water as New York. It has about 300 or 400 times the installed capacity of solar as New York. To me, the physics of the situation speaks for itself. The solar resource is huge. Solar cells are made from the second most common element on Earth, silicon. And each time factories increase production by a factor of 2, the cost of solar cells goes down 20%. That has been happening for the last 30 plus years. What's new right now is that the doubling time is only 1 to 1.5 years. While we have been sitting around talking about clean coal and natural gas, the cost of photovoltaics has gone down 25% in just the last 6 months. Wake up, America. The sun is